Okay, boys and girls, welcome to Insertion Sort. AP has three different sorting methods: selection sort, insertion sort, merge sort. Unfortunately, it does not have Mr. Westphal's favorite sort, which is called counting sort, which is, by the way, way better than these other loser sort methods. But at any rate, the ones that the AP decided to test you on are these three. So we're going to go over insertion date. You can think about its big O notation. Kind of think in your head, is it going to be faster than selection sort, slower? Kind of think it through as we're going through this lesson. All right. Yeah, so that's what this is telling you to do here. All right. So I'm going to explain it with cards as best I can. So you have these scrambled in order, right? And we're going to order them from least to greatest. And so how insertion sort works is it sort of says the first position is a sorted list. All right, it's only got one item in it, and it's sorted in order from least to greatest. Okay, and then what it does is it takes the next one over and says, okay, I'm going to make a list of two things in order, and I want to insert the jack in the right position. Okay, so what it does is it kind of moves down here and says, this is the item we're trying to insert, and then it'll say, is this thing greater than the one on the left? And if it is, then it just slides it back into place. All right, and so not really much happened there, but now that one, the first two are considered sorted. Okay, and then it takes the next one and it's going to insert it into the list. So it makes it an insert item, and then it says, is this one greater than me? If it is, move it over one. Is this one now greater? Yep, move it over one. And then we've got to the very end of the list, so this must be my home. Okay, and then at this point we've gone through it twice, and now we have a list of three sorted things. You can see these are sorted in order. All right, now it takes the next one and says, okay, I'm going to insert it here. I got to figure out the right position, and any cards that are bigger than me, I move to the right. So this one I move to the right one, and then I say, okay, now 9 is not bigger than me, so I must have found my home. So I'm going to move the 10 right there. Okay, and now those four cards have been sorted. The queen is going to go down, and it doesn't do many comparisons here. It just comes down and says, oh, nope, the jack is not bigger than me, so I put myself right back here. All right, so that was kind of pretty efficient, pretty quick. And then one more time, this is really what it looks like, is the 7 comes down and says, okay, anything that is bigger than me is going to move to the right. So move the queen, the jack, the 10, the 9, and I keep going until I hit either the end of my array or I finally hit one that's actually less than me. So in this case, the 3 is less, and so the 7 gets slid into position 1. All right, and now the whole thing is sorted. All right, so it's called insertion sort. And you could try and think about what does the code maybe look like, what you think the algorithm would be. All right, and so our goal today is really just to understand it, make some sense of it. So along those lines, here's a set of some cards, and see if you can kind of walk through what it would look like, right? If you happen to have a deck of cards, you could get out a deck of 5, 6 cards and then scramble them and see if you can do insertion sort with the cards. And then I'll be back with you once you've thought it through. Okay, so I'm going to get insert item. I should have copied this over to the other one. All right. When it starts, the first thing is considered sorted. So the 10 is already considered sorted by itself. Then it's going to bring down this 2 and say, okay, anything bigger than me moves right. And then I hit the end of the array, so I'm going to slide myself in there. These 2 are now sorted. Okay, and I might not do all of this just because it kind of gets obnoxious. But then the queen comes down. Nothing is bigger than me, so I just slide on back. Now we have 3 things sorted. Okay, and then we move to the 7, bring it down and say, okay, blah, 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 anything bigger than me, shift over. Nope, the 2 is not bigger than me, so the 7 must go there. And now these 3 things are sorted, right? And we only actually looped 3 times because the first thing is already considered sorted by itself. So that's 3 loops. So we have 2 more loops to insert the 8 and the 5, right? And just to not be obnoxious, I guess I could go speed mode. It'd go, see if I can do the speed mode. And slide anything over. It's bigger. Goes the 8. This is now sorted 5 times. Bring it down, slide stuff over, zoom, zoom, zoom. So it's just copying them over, one spot over in the array, and boom, the 5 goes there, and boom, we're done. Okay, so I do think it'd be good at this point to pause the video and try and think of how you'd explain insert algorithm in your own words. How do you explain it to a parent or something like that? Like, what are the steps for this algorithm? And so pause it before you see my answer. You don't have to write it out at this point. I'm gonna have you do that in the homework assignment, but just at least think it through right now. Talk it out loud or find a friend. All right, so this is Mr. Westpatal version of it. We have an outside loop that starts at position 1 and goes all the way to the last position, length minus 1. To be length 6, so minus 1 would be 5. Set the insert item to be the position we're on, and then loop backwards. If the insert item is less than the value at each position, shift that element 1 forward, and once the insert item is greater than that value, insert into the position 1 ahead of the position we are checking. It's a little bit wordy, but we're always checking 1 back, and if it needs to be shifted, we shift it. Otherwise, we insert it into that position we're checking against. Is the idea. So just to visualize it, here's the online site. I put a link to it in today's folder. If you want to play around with it, I think this is a really good for understanding insertion sort. Right, so I'm going to hit play here, and I want you just to think after 1 time through the loop what would happen. All right. Hopefully I have your answer. And the idea is 3 is already sorted, so it's going to insert the 44, but 44 is already in the right spot. Right, so that'll happen the first time. Then the second time through, we should see the 38. The 44 will get shifted over, and the 38 will go in its place. Okay, so yep, it already is in place, shifted over, now it goes. Here comes the 5, shift over anything that needs to be shifted until you find the right spot. Sometimes you find it really fast, which is good for efficiency, right? Like 36, we only have to compare 3 times there. 26, we'll have to compare once, twice, 3, 4, so we'll do 4 comparisons. 27, looks like 1, 2, 3, 4 comparisons. The 2 we're going to need to do a bunch because it's got to shift all the way down. So sometimes we get lucky, sometimes we don't. So as far as efficiency goes, it actually does depend on what the array looks like at the start. There's a lot of work. The 46, though, is real quick. Only 2 comparisons, right, till we find its home. I might have been miscounting those comparisons earlier because you do have to compare. Like here we compare to the 3, right? So 19, we'll have to compare to 15 before we know it's home. So it compares to all of these. It does compare to 15, now it goes in its home. All right, and that's it. We got them all sorted. So again, you can play around with this if you want. I think it's a really good way to help you understand insertion sort. Okay, so I really want to focus now on like how many comparisons, because that's what they'll do on the AP test is like, here's our array. We're going to do insertion sort, how many total comparisons we'll need. And as I was just showing in that algorithm, it really depends, or on this website, it depends on what the array looks like at the start. Okay, so to figure it out, you have to sort of go through step by step, right? And so if we're doing the 4, for inserting the 4, we have to compare just once to the 13, so that the 4 will end up here, getting inserted there. 13, 9, 11, 7, 6. Okay, now these 2 will be sorted, right? And that was only 1 comparison. Okay, and then when the 9 goes, we are going to shift just the 13 over, but it does have to compare to 4 because it doesn't know if the 4 needs to shift or not. So the 9 will come down, compare to the 13, compare to the 4, and then go in place of the 13. Right, so even though only the 13 had to shift, we did take 2 comparisons there because we did have to check the 9 against the 4. Okay, these are all sorted, so now the 11 goes, it'll compare against 13, and it'll compare against 9 until it finds its home. So it would go 4, 9, then it finds its home 1 right of 9. So let's see, so 11 would be there, now 13 would be here. Okay, and so that was 2 comparisons again. Okay, now the 7 is going to compare against all of them actually. So all the sorted ones, it compares here, shifts, and then it will go here, but it does have to compare against the 4. So I'm going to write down here, that's 4 comparisons, just so I don't forget. Now 7 will be in its right spot. And then last, the 6. And again, the 6 is going to compare against all of these, and it will even compare against the 4 before it finds its home. Right, so that's going to be 5 more comparisons to get the 6 into the right spot. Right, and obviously it'd just be 4, 6, 7, 9, 11, 13. Okay, and so then our total comparisons, just add those up, right, and that should be 14. Okay, and so hopefully you're thinking like more efficient, less efficient than selection sort, right? We'll time it tomorrow, and then you can kind of try and determine it that way. But based on this, hopefully you have some intuitive sense of which one would actually be better. Between, you could think about what selection would do here, right? You'd select the lowest for this spot, then the next lowest for this one, et cetera, et cetera. And is that more or less efficient than insertion sort? Good follow-up question to what we were just talking about is, this is the worst case. Oftentimes when you do big O, they talk about the worst possible case. So if the elements are in reverse order, that's going to take the longest amount of time or comparisons to sort. Right? If they're already in order, you just compare one. Each one only compared once before you find its home. So pause it here and see if you can figure out how many total comparisons would be needed. Okay, so hopefully there's a pattern here. So 12 would only need to be compared once against 18. And then 11 to slide in place would have to be compared to the 2 previous before it finds its home at the start. And then 9, again, would do all 3 previous before it finds its home here. 7, same thing, would be 4. And 6 would be 5. So if we add all those together, then the worst case, that would be 15 comparisons would be needed to sort this array of 6 elements. Okay, last thing I got for you is the code. So I'd encourage you to pause it here and see if you can make sense of what is this code doing in terms of insertion sort. Right? It's a method and then passing an array, but what are each of these little parts? See if you can make some sense of it. All right, so here's our big loop that starts in the first position, and then it loops all the way to the last position, going by 1. This sets the item we're trying to insert. And then this says what index, where are we going to insert it at? What is the index that's possible? And you always start 1 back from where you're at, right? So to try and make this simple, I have a picture down here, right, where we've already sorted the 0, 1, 2 spots of this array, and now we're going to do this 5 next. All right, and I'll reference that in a second here, I guess. So this says while possible index is greater than or equal to 0, right? Because you don't want to run off the end of the array here. And if insert item is less than the array possible index, so if our item is less, then we want to shift it. So this code just shifts the bigger elements 1, right? And then that's no longer the possible index, so we move that back 1, right? And then once this loop breaks, we know that we either have hit 0 as our possible index, or we've hit a spot where we're bigger than the 1 to the left of us, and then we actually want to insert the insert item into the spot, 1 spot of where we're checking. So to try and make sense of this code, right here, if we were right here, we'd sorted these. Think about what would be insert item, what would be the first possible index we would start at, and then kind of think, I guess, through the rest of it, what would happen. Okay, so hopefully your answer here will make some sense. So we would have I would be 3 at this point because that's the spot we're trying to insert. The index we're trying to insert is 3. So insert item then would be the value at position 3, which would be 5. So we're inserting the 5 essentially. And then possible index would start at 1 less than I2. So this would be the first possible spot where the 5 could go, right? And so it would run a couple times, and this line here would shift the 8 over 1 spot. So basically array position 3 would become array position 2, and then the 7 would shift 2, right? Possible index would go minus minus 1, and then we would shift array position 2 would become array position 1, and then finally this check here for 3 would make the 5 be inserted here. All right.